Integration by parts. It's traditionally taught in a complicated manner, full of u's and v's and du's and dv's, but I have developed an approach that makes it easy, and really clean too. In this video, I'll explain both how and why my approach works. In a footnote to my book, Full Frontal Calculus, I jokingly refer to my method as braver arrow notation, the joke being that it's considered uncouth to name something after yourself. Well, what can I say? We live in uncouth times. A less self-aggrandizing name might be integration by parts with arrows. But before we get started on the easy way to integrate by parts, I should remind you of the traditional way we think about integration by parts, the tedious way. By the way, if you are completely new to integration by parts, don't worry if this brief review means nothing to you. Just notice how involved it is, which explains why I want to offer a better way. Anyway, let's apply the traditional technique to the function x cosine x. Once we decide to apply integration by parts, we must introduce two new variables, u and v. And to do this, we set up a little dictionary. We identify one part of the integral as our u and record it. We call the rest not v, but dv and record it in our dictionary too. Next, we look at our u and do some calculus manipulations to get an expression for du. Then we turn our attention to dv, do some more calculus manipulations, which then gives us an expression for v itself. Our dictionary is complete. With it in hand, we can now apply the integration by parts formula, which is something you memorize. The first term, uv, can be obtained from our dictionary, so we write that down. The second term also comes from our dictionary. Now we just bring down the first term, do the integral in the second, put a cherry on top, and we are done. That's the traditional way of doing integration by parts, and you can see why it can drive students a little crazy. In contrast, I'm going to show you how to do integration by parts with no u's, no v's, no du's, no dv's, and no dictionary at all. Everything will stay in terms of x. You won't get lost anywhere in the process, and the technique will feel natural before you have even finished this video. So, enough of the traditional tedious method. Before I can show you how to do integration by parts with arrows, I'll need to introduce a little notation and terminology. It isn't official notation and terminology, it's just something I've invented to help us with our bookkeeping. It will also help you understand exactly when integration by parts is an appropriate technique to use. So let's bring back the function that we were integrating before. The first thing to observe is that it's a product of two functions, x and cosine x. Every application of integration by parts begins with identifying two factors of the integrand. One of those two factors should, ideally, become simpler when we take its derivative. In this case, that would be x. I'm going to draw an arrow from x, pointing down to its simpler derivative, 1. As for the other factor in the integrand, cosine x, we want to think about its antiderivative, which is sine x. I've drawn that up here, floating in space, so that I can draw another arrow, also pointing down to its derivative. So notice what we have, two stacks of functions. In each stack, taking the derivative of the top function yields the bottom function. Whenever we have a setup like this, I'm going to call it an arrow-marked integral. Notice that we can mark the same integral in different ways. For example, in this integral, we could have begun by noting that the derivative of cosine x is minus sine x. In that case, we'd need to think about the antiderivative of the other factor, x, which is, of course, x squared over 2. This, too, is a perfectly legitimate arrow-marked integral. Or take a different example, the integral of e to the x sine x. If we want to fire some arrows at it, one way would be to note that the derivative of e to the x is, of course, e to the x, while the antiderivative of sine x is minus cosine x. And now we have another arrow-marked integral. But we could have done it the other way, first observing that sine's derivative is cosine x, while e to the x's antiderivative is e to the x. This too is a legitimate arrow-marked integral. Okay, you now know what an arrow-marked integral is, but what is the use of marking up an integral this way? The use is that it can show you at a glance whether integration by parts will even work on a given integral. The idea is to compare the function we want to integrate, such as x cosine x, with the two outer functions in our arrow-marked integral. That is, the ones that we have penciled in. If the product of those outer functions, and here that product is just sine x, is something that you know how to integrate, then integration by parts will work. I'll explain how to carry it out shortly, but for now it's good just to recognize when integration by parts will be appropriate. Anyway, let's compare our second arrow-marked integral. In that one, we were also trying to integrate x cosine x. Will these arrows help us with integration by parts? Well, look at the outer functions. Their product, minus x squared over 2 sine x, is not something we can readily integrate. In fact, that function is more complicated than the original integrand, since it's the product of a trig function and a quadratic, as opposed to the product of a trig function and a linear function, which is what we had originally. Thus, this choice of arrows will not lead to success with integration by parts. Finally, let's look at the third arrow marked integral on the screen, the integral of e to the x sine x. In this case, our outer functions have a product, e to the x cosine x, that has the same order of complexity as the original integrand. Neither simpler, like the first integral was, nor more complicated, like the second one was. In this case, it's unclear, for now at least, whether integration by parts can help us crack our integral. We'll return to this question at the end of the video. Okay, at this point you know what an arrow marked integral is, and you know how it can tell you whether integration by parts is likely to help us. That means you are finally ready for the statement of the integration by parts theorem when it's done with arrows. So, the theorem tells us that any arrow marked integral, such as this one from our previous work, is equal to something minus something. Namely, the theorem states that any arrow marked integral equals its top product, which I'll explain in a few seconds, minus its outer integral, which I'll also explain, though you can probably guess that one's meaning already. So let's unpack this in the particular context of the arrow marked integral on the screen. According to our theorem, it equals its top product minus its outer integral. Well, what is meant by its top product? Remember how I said we had two stacks of functions in an arrow marked integral? If we take the top function in each stack, their product is the top product. That's all. But the theorem says that any arrow marked integral is its top product minus its outer integral. What's that? The outer integral is the integral of, exactly as you'd guess, the product of the two outer functions from the original arrow marked integral. And that's it. Having now applied the integration by parts theorem, we finish the job by doing that outer integral and putting the cherry on top. And we are done. If you understood how that worked, you know how to do integration by parts with arrows. No u's, no v's, no dv's, no du's. You just fire two arrows and remember one sentence. An arrow marked integral is its top product minus its outer integral. Piece of cake. Let's do a few more examples to get used to it, and then I'll prove the theorem. So let's look at the integral of x squared log x. You might think, aha, x squared has a simple derivative, and indeed it does. But what is log x's antiderivative? That's not one most of us know off the top of our head, though we will figure it out soon. Anyway, firing our arrows this way doesn't look very promising, so let's adjust our aim. This looks better. The derivative of log x is 1 over x, which combines nicely with x squared's antiderivative of x cubed over 3. Their product is a quadratic, which is easy to integrate, so integration by parts will work here. Namely, this arrow marked integral is its top product, which is going to be x cubed over 3 log x minus the outer integral, which is the integral of x squared over 3. The rest is routine. Bring the first term down, do the easy integral in the second term, and put the cherry on top. That's it. Integration by parts is easy when you do it with arrows. But let's return to a question we raised earlier. What is the antiderivative of the natural logarithm function? This doesn't look like the sort of integral that integration by parts could crack, since it doesn't involve a product of functions. But if we are clever, it does. By inserting that factor of 1, we pick up a second factor. Now let's fire those arrows. Log x's derivative is 1 over x, and 1's antiderivative is x. The product of the outer functions is easy to integrate, of course, so this is indeed a job for integration by parts. The top product is x log x. From that, we subtract the outer integral, which is the integral of x times 1x, or 1. The rest is straightforward, and we now know the antiderivative of log x. It's x log x minus x, as you can confirm by taking its derivative. It's amazing how much mileage you can get in mathematics just by multiplying by 1, or sometimes adding 0, in strategic, creative ways. Well, let's do one last example before we turn to the proof of integration by parts theorem. Let's try to integrate x squared e to the x. It looks like there might be a promising choice of arrows here, since the ones I've just fired on the screen will make the product of the outer functions simpler than the original integrand, which is what we want. Instead of trying to integrate a quadratic times an exponential, now we'll just need to integrate a linear function times an exponential, which is at least a step in the direction of simplicity. Anyway, the top product here is x squared e to the x, from which we must subtract the outer integral, which is the integral of 2x e to the x. Now this has a simpler integrand than our original integral, but it's still not obvious at a glance what its antiderivative is. What to do? Fire your arrows again, of course. Looking at the outer functions here, we see that their product will be easy to integrate, so this will work. Thus, assured of eventual victory, we bring down the first term and set up parentheses to hold the fruits of our labors. This second integration by parts gives us a top product of 2x e to the x, from which we subtract the outer integral, which is the integral of 2e to the x. Of course, that function's integral is itself. Distributing that negative and factoring out the common e to the x, we obtain our answer. Good. By now you may feel like an expert in using integration by parts, but a nagging thought should linger in your mind. Why does it work? Well, let's discuss the proof of the integration by parts theorem. To see why it holds, we'll first need to translate our statement into more conventional symbols. We'll begin with the notion of an arrow-marked integral. This, of course, is the integral of a product of two functions. Instead of calling these functions f and g, as you might expect, I'm calling them f prime and g to remind us that although we're interested in the derivative of one of them, we're interested in the antiderivative of the other. Anyway, now we have our symbolic representation of a general arrow-marked integral. The theorem claims that it is equal to its top product, which according to the symbols we're using will be f of x g of x, minus its outer integral, which is the integral of f of x g prime of x. If we now get rid of the arrows, which are just scaffolding to help us implement the theorem, we're left with a purely symbolic version of the integration by parts theorem. Let's use it to reformulate the theorem in a language that's less memorable, but also much more amenable to proof by mere symbol pushing. This reformulated version is the same theorem, just re-expressed in a language in which we are already fluent. Still, how are we going to prove it? We'll get our first big insight if we ignore some of the symbols here and just concentrate on the functions that this theorem claims to relate. They should remind you of something. Namely, if we take the derivative of the central function, f of x g of x, we know that we'll get the sum of the other two functions. That's just the product rule from your first calculus class. This suggests that the product rule might be the key to proving the integration by parts theorem. And indeed it will. If we start with the product rule, our strategy will be simple. Take this term, f prime x g of x, which also occurs prominently in the integration by parts theorem, and isolate it on one side of the equation. In fact, let's put it on the left side to match our target equation in the box. The next thing we need to do to match that target is, of course, to integrate both sides. This is looking good. Now we'll just split that integral on the right into two integrals, the first of which is the antiderivative of the derivative of a function. Those operations undo each other, of course, leaving us with the function. And once we remove those parentheses, we see that we've got it. We've matched the target, so we have proved the integration by parts theorem. Excellent. I could stop the video here, but as a little bonus, I want to return to an integral that we encountered in passing already. When we first met it, we weren't sure if integration by parts could help us, because when we fire our arrows at it, we end up with outer functions whose product is precisely the same order of complexity as our original integrand. So what should we do? Just give up on integration by parts and try something else? Well, maybe, but first let's try integration by parts and see what happens. Of course, we get the top product minus the outer integral, and of course, it's that outer integral that makes us skeptical. I mean, what are we going to do now? Try the same thing again? Sure, let's try it. I'll set up some brackets to hold the results of our second application of integration by parts. As always, we get the top product minus the outer integral. Now let's clean up the mess by turning those two negatives into a positive, and then getting rid of the brackets by distributing the negative in front of them. Moreover, let's take down the scaffolding that got us here, and we'll just look at the equation we have developed so far. Here's something interesting. The integral we're ultimately interested in appears twice in this equation, and they don't cancel each other out. That means we can just solve the equation for the integral in the blue box. In fact, this may be easiest to see if I put the remaining stuff in a red box so that we just have blue is red minus blue. To solve for blue, we just use elementary algebra. Bring the right blue term to the left side of the equation so that two copies of blue are over there, and then divide both sides by that 2, and we'll find that our blue integral is just half of the red stuff. Or, to look more respectable, we'll drop those colors and put the cherry on top. Excuse me, the C, since we're being respectable. A remarkable technique. Our integral, our blue snake, managed to swallow its own tail, leading to a happy conclusion after all. Thanks for watching, and if you think you might enjoy more of my approach to calculus, do check out my book, Full Frontal Calculus, An Infinitesimal Approach. Good night.